Hey guys, hello everyone. Welcome to Rasayan Academy. So we are starting a new series, all new series of question practice, and that is solely going to be based on the name reactions. So we have already completed a lot of name reactions. There are yet some name reactions to be added in the 100 name reaction series. But since we have done so many name reactions, a practice series has to be started. And yes, I am starting year-wise practice series. Basically, we are going to be starting right from 2011, and definitely you are practicing the questions by yourself as well. I hope that this series is going to be helpful for all of you. We are going to do the same series for CSI net as well as gate examinations, identifying all the important name reactions so that you can complete this topic. Also, name reactions, doing this topic does not require a lot of other topic information. Name reactions you can do directly, and along with this, if you know a little bit of organic reagents, it is going to make sure that you score a lot of marks in the exam. Okay, so yes, today we start this series right from June 2011 question. Definitely we are going to do the new questions starting from here. Okay, so the first question is very simple. What you have to do is stop the video and identify the question by yourself. Which reaction is this? Also comment in the comment section that this is question number one. What is the first reaction which is going on, right? So yes, you are done by yourself. We are going to start the discussion of this question. Okay, so yes, the first question that we are doing over here is your Sonogashira reaction. How do we know? We have also discussed this reaction. It is Sonogashira reaction. Alright, and it is a palladium catalyzed coupling reaction in between the aryl halide as well as the alkyne. Okay, the terminal alkyne. Alright, so let's start discussing the mechanism. So first of all, what happens is the palladium is there in the zero oxidation state. As always, it is going to undergo the oxidative addition in between the aryl halide bond. Now it becomes +2 from 0. Okay, there are these phosphine ligands, but we are not drawing it for the sake of simplicity. Also, you have this terminal alkyne over here. So terminal alkyne in the presence of a base is going to lose this proton and going to combine with this copper to give you this kind of a molecule. Alright, and definitely since there is a base, this O is also going to become O minus, but copper +1 is present due to soft interaction. It is going to connect to the carbon, not to the oxygen. Okay, so you can just directly write in this way the reaction is going to proceed. You can write O minus, you can write OH, the same thing. Now what happens is, guys, obviously since you have already done the oxidative addition over here and the replacement of proton by copper, the only step that remains is transmetallation. Okay, so you are going to do transmetallation after the oxidative addition. That is, metallation is the exchange of the ligand from one metal to another metal. Alright, so this copper over here is going to leave this group with palladium, and it is going to eliminate as copper iodide like this. Now the palladium is going to do reductive elimination, and it is going to make these groups connect as it is. Alright, so the palladium has left, let's say it has left, and this is what you have. Palladium is now once again in the zero oxidation state. It was +2 over here. So you are going to get this kind of a molecule. Now still you get the alkyne system, guys. Yes, let's say we are having the aqueous workup over here in the last step so that it converts to the OH group. But you still have the alkyne, and in your option it is not present. Now in the last step, in the presence of lithium aluminium hydride is very famous for the propargyl alcohol reduction. Just like you have the allylic alcohol in this way, alright, you also have the propargylic alcohol, that is your triple bond, one saturated carbon to this saturated carbon, your OH is connected, right? So propargyl alcohol, this is your molecule, propargyl alcohol. Once again, very famously, it is going to reduce this to give you a transallylic alcohol. It gives you a transallylic alcohol from here. Okay, So C is going to be your correct answer. What is this name reaction? It is your Sonogashira reaction starting from June 2011. Alright, palladium catalyzed reaction. Very, very simple. Let's move onwards to another good reaction. Question number 2 it is, in the following reaction sequence, the correct structure for the major product X and Y are. Once again, June 2011. Just stop the video and do it by yourself, guys. So, in the presence of a weak base like K2CO3, it is not a very strong base over here, but what happens is the protons which are present on these carbons, they are acidic protons, isn't it? So if it is an acidic proton, it is going to give you nitroenolate just like it gives you a normal enolate, okay? It is going to give you a nitroenolate in this way, just like a enolate is observed, alright, in this way. And now what is it going to do? It is going to do the Michael addition towards this molecule. The nitroenolate is going to do Michael addition towards this molecule, and the connectivity is somehow going to be like this. Alright. So let's say this is O minus, but once again it is going to grab a proton from the system, and I can directly write this molecule over here. There is going to be this ethyl group on this side and one methyl group on this side. Now in the next step you see there is hydrogen 10% PDC, which means this is going to convert the nitro group into the amine group. So Me C double bond O Et, and definitely the carbonyl group does not reduce in the presence of hydrogen palladium catalyst, right? No, it doesn't happen. So 1, 2, 3, 4, and 5. Now the nitrogen could attack over here onto this carbonyl carbon. But the question is about the stereochemistry. So till now it is very, very simple. Your reaction is nothing but very similar to the Henry aldol reaction. Henry nitro aldol reaction. Alright. However, it is not the direct aldol reaction because here you are doing Michael addition, not attacking on another aldehyde. But yeah, it is very, very similar to the Henry nitroaldol reaction. And in the next step, let's say we draw the next step in this way. So you have one methyl on this side, there's your NH2 group, and on this side there was your carbonyl and the ethyl group. Okay. So the nitrogen is now going to attack on this carbonyl carbon, and the stereochemistry which is favored is going to be trans. Why? Why is it favored trans? Because there will be less interaction between these two methyl and ethyl groups, definitely more favored. Alright, and the OH is going to, this is going to become OH, and once again the nitrogen is going to eliminate this group in this way to give you the intermediate imine system like this. Alright, so the imine is once again planar. Imine is also once again planar. Now the hydrogen which transfers can transfer in such a way that you are going to get the least or the most stable and the molecule with the least steric hindrance. So methyl and ethyl are going to be trans to each other. Alright, so your molecule in the first case, it is simply your nitroaldol formation followed by the Michael addition gives you this molecule. Okay, and the product Y is going to be a 5-membered cyclic ring, and also the stereochemistry will be trans, more favored like this. Okay, very simple question. Let's do this one from December 2011. Now just looking at this reagent you must be able to identify CBr4 and phosphine. Now the same reagent is used in two reactions, the Apple reaction as well as the Corey-Fuchs reaction, right? But it is this reaction when you have Corey-Fuchs reaction when you are starting from an aldehyde, okay, and then in the next step you have excess of butyl lithium in this way. Alright, excess of butyl lithium. So let's see what is this overall reaction. First of all, what happens with CBr4? Let's see. You must be able to, from this combination, you must be able to draw the mechanism to generate the ylide. This is PPH3 Br. Phosphorus gets a positive charge since it has attacked the bromine. CBr3 has a negative charge from which it is going to attack the phosphorus Br minus leaves. So CBr3 and PPH3, where the PPH3 phosphorus has a positive charge. Now there is a Br minus which is free. Alright, let's say I write all the Br in this way. I'm writing all the bonds in this way. And there is one Br minus which is free from here. So this is going to attack over one of the bromines and gets a negative charge on the carbon. That gets a negative charge on the carbon. So I can rather write the molecule in this way, and you can also write the molecule in this way. Double bond PPH3. Alright, so this is going to be your ylide system. Yes, isn't it? Carbon based ylide. Now this ylide, just like your Wittig reaction, through the oxidane intermediate, through the betaine intermediate, is going to attach to the CHO group. Let's say you have RCHO. I have named all of this chain as R. Okay. You have RCHO. So just like your normal Wittig reaction, it is going to add in such a way that you eliminate the phosphine oxide and you add this molecule. Alright, plus eliminate the phosphine oxide, PH3P double bond O, in this way. Alright. Now what is the next step, guys? You are having excess of butyl lithium. Now butyl lithium is first of all going to behave as a base so that the HBr can eliminate from the molecule. The HBr has eliminated, and this is what you get: terminal alkyne bromide in this way. Now one more step of butyl lithium, that is going to do halogen exchange reaction and gives you RC triple bond C. And first of all it gives you minus and lithium plus. On the aqueous workup it is going to give us the RC triple bond CH. Okay, so that gives you the alkyne, this molecule. So A is going to be an alkyne and the name reaction is Corey-Fuchs reaction. Very well, but is it going to end over here? No, we have another step also. Let's proceed from here now. Alright, in the next step you have phenyl azide. This is what you have, phenyl azide. What is this phenyl azide going to do? Let's say I have the, once again, the alkyne, the terminal alkyne in this way. So to the terminal alkyne, the azide is going to behave like a 1,3 dipolar compound, and it is going to add in such a way okay, it is going to add in such a way so that you get the 1,4 product. Alright, these two are going to be far away from each other, as much far as possible. Alright, and in the presence of CuSO4, that is your copper 2 plus salt, this 1,3 dipolar addition in the presence of copper salt, alright, this is going to be known as the click reaction. Okay, this is going to be known as the click reaction, and your answer is option number D. Very, very simple question, December 2011. Corey-Fuchs reaction and click reaction. Next reaction from the same year goes like this. Correct sequence of reagents you have to find out for the following transformation. So it's so easy. The product is given and the reactant and product both are given. What is A to D that you have to find out? Alright, so let's look at this. See, if you have done these reactions properly, you won't be worried about what is going to happen. You know it is Eschen-Mosher fragmentation reaction, right? Why? The whole chain opens up. Okay. So in the first step, how are you going to do the epoxidation of the alpha beta unsaturated carbonyl? So we have to provide O minus nucleophilic oxygen has to be provided. Then only it is going to undergo the epoxidation on the carbene on the alpha beta alkene position. Okay, in this way. Now the epoxidation has taken place. Metachloroperbenzoic acid is of no use at all to this system because it transfers electron deficient oxygen. And here you need an electron rich oxygen. So definitely metachloroperbenzoic acid not required. Now what happens in the next step? In the next step you see oxide is still there and you are going to generate NH and TS this way. Alright, in this way you are going to add these two groups. Now what guys? Now there has to be the proton removal in this way. Proton removal in this way is going to have O minus over here. O minus is free. There will be one double bond on this side. Alright, and to this N double bond NTS is going to be connected. Now break the bonds all from here. O minus is going to become oxygen carbon double bond. This bond, carbon carbon bond opens up, and this is the shift in the reaction. See what is happening. What is happening over here? You have fragmentation. Very beautiful reaction this is. You have fragmentation, and after fragmentation, see I am writing the molecule in the same way so that we can correlate better. Alright, in this way. Alright, so what just happened? There is a triple bond which is created, and triple bond cannot be cis on trans, so it is a linear triple bond, right? Now in your product the reaction is the same, the groups which are attached is the same, everything is the same, it's all good. But what happens is you require cis alkene. What are you going to do? Alkyne reduction to cis alkene only happens with the Lindlar's catalyst. So Lindlar's catalyst, you know, is it's only the hydrogen palladium charcoal, but in the presence of a catalyst poison, so that alkyne to alkene reduction stops. It does not further reduce to the alkane. Okay, so through the Lindlar's catalyst, you are going to have selective reduction, and that also syn. Alright, so that's why it gives you the cis alkene. Very, very simple reaction. Answer is option number D. It is Eschen-Mosher fragmentation. Alright, and this has been asked plenty of times in your CSI and NET and GATE exam, all the exams. Okay, and finally you have the Lindlar's reduction. Okay, right. Answer is option number D. We move onwards to another very nice question. Major product A and B in the following reaction sequence are. Yes, what happens to this? So we have done how many questions? This is your question number 1. This is question number 2, 3, 4, 5. Alright, fifth question. The major product A and B in the following reaction sequence are. Once again, stop the video, do it by yourself. Alright, so here you see you are going to have this ylide PH3P double bond CHCOOET. Alright, this is your ylide guys, but there's something special about this ylide. It is a stable ylide. How do I say it is a stable ylide? Because when you break the pi bond, of the ylide, you say it is positive and the carbon has to be negative. So because of that there is going to be resonance, and when there is resonance in the carbanion part of the system, you say it is a stable ylide. So in the Wittig reaction, this is your Wittig reaction, name reaction. So in the Wittig reaction, the stable ylide will prefer to give you the E alkene. Okay, so you are not getting this, not this, and ये तो absurd है, no double bond. You are going to get option number D. Alright, trans alkene. Just by one option, the answer is done. Okay, but anyways, we are going to look at the other reaction, the protection of the alcoholic group. So who is this molecule? It is dihydropyran. Okay, so it is going to be your 2,4-dihydro or 2,3-dihydropyran. Yes, and what happens is it is going to be attacked by the alcohol. Now there it is. Let's see how the attack is going to take place. So this oxygen, this is going to attack over this carbon. You are going to have a new bond. Proton is being taken away by this carbon. This is it. This is what you have. This proton has could transfer over here also, or the solvent proton could also be taken. That doesn't matter. So your answer is option number D. First of all, Wittig reaction, and second, you are going to have the protection of the OH by the dihydropyran molecule. Okay, very well, very simple, guys. Let's move on to question number 6. Another simple question from December 2011. Major product A and B in the following reaction sequence are. So what do you have? Lithium and liquid ammonia in the presence of a polar solvent. Is it the Birch reduction? Yes, it is the Birch reduction. What will the Birch reduction do, guys? In the presence of 1-methyl or ethyl or ethoxy, all the electron donating groups. All right. What will happen? The electron will be transferred over here in this way. Yes. So you are going to give the reduction of substituted benzene in this way. Okay. This is your substituted benzene where you are going to give the reduction through the Birch reduction. Okay. Now what happens is you have two double bonds. Metachloroperbenzoic acid is only one equivalent. It has to give the oxide over there. What will it do? Yes, it is going to give you the epoxide over here. Exactly. Not on the other one. Why? Because the reaction looks for the electron-rich carbon-carbon double bond. Alright, this reaction is also looking for the carbon-carbon double bond electron-rich ring. So epoxide formation, Birch reduction like this. Alright. Okay, just a second. This is OMe. Yes, this bond is used, so you have double bond O on this side. So this is your correct answer. Option number B. This is wrong because here the double bond position is different. It's absolutely different. Okay. And yes, you are not going to do the epoxidation on the electron deficient carbon-carbon double bond as compared to this. So ये wrong हो गया. Moving on to seventh question. Very, very important. Plenty of times it has been asked. Once again, December 2011 only. Right. The correct reagent for the for affecting the following reactions are. So basically, if you look at these reactions, two of them are cyclopropanation and one of them is the epoxide formation. Okay, so let's see. Option number A must be doing the 1,4 addition. Yes. Option number B must be doing the 1,2 addition, right? And it is going to be through the same type of reagent. Okay, so when you are having the sulfoxide and sulfoxonium ylide, ये देखो, sulfoxonium ylide and sulfonium ylide. See, so what are they going to do? They are going to give you these two reactions. ठीक है? So that falls under the Korechkovsky reaction. Very, very important, and it is covered under the name reaction series. So this is going to give you 1,4 addition, the sulfoxonium ylide, and the sulfonium ylide gives you the 1,2 addition. So this is 1,4, this is 1,2. A option is going to be this. This is going to be A right over here. Alright, sulfoxonium ylide. And B is going to be over here, 1,2 addition. What about C, guys? C is going to add to the most, I would say most electron rich, because alpha beta unsaturated systems are not electron rich, so this is going to be provided the most electron rich as well as most isolated double bond. All right, yes, this is the most isolated, far away from the main system. That's why the reaction happens very clearly. This is going to be your product, option number A. Alright, very simple guys. Selectivity in reagents. This is your Korechkovsky reaction. That is what we have done first. Alright, in our name reaction series. Now, yes, this was question number 7. Now, let's do question number 8. Once again, very, very important. The major product A and B in the following synthetic reaction sequence is. You have to identify this once again. I see that there is a aryl halide and I also see that there is a catechol borane. Absolutely, it is a Suzuki coupling reaction. Okay, it is a Suzuki coupling reaction. How does the coupling reaction proceed? To the aryl halide, your palladium, which is there in the zero oxidation state, undergoes to +2 oxidation state, causing the oxidative addition. So there you are going to show it. Okay, sorry, there is an iodine over here. Now, yes, what is going to happen, guys? Boron can transfer this group over to the molecule. Okay, followed by reductive elimination in this way. This is what you get. All right. Now, definitely there is hydrolysis. So, who is going to do the hydrolysis? We have not written the ester parts or the amide part over here. Okay, in this way, like this. So, in the presence of hydrolysis step, in the presence of water, this OAT, water is going to attack over this carbon. Bond opens up, but when it falls back, OAT is a good leaving group. Okay. Okay, so this is going to be COCH3 double bond, and you will also have an OH on this side. Alright, so now the nitrogen can attack on the, not the enol, but definitely on the carbonyl system. So you are having the enol system over here. What you are going to do is you will first just write the carbonyl in this way, and then your nitrogen is going to attack on the carbonyl in the presence of a little bit of acid. That gives you 1, 2, 3, 4, and 5. That also gives you a 5-member ring system like this, and since there is OH, the OH is further completely removed and gave you a double bond. Okay, so C is going to be your correct answer for this option, question number 8 as well. This is a Suzuki coupling reaction. We have also done this reaction in the name reaction series. So yes guys, please check out all the important name reactions, because this maximum question practice series has already ended. We are going to have all the questions from June 2011 to your latest or later years questions. Alright, and we are also going to see some gate question. We have already done the TIFR questions. Okay, so please check them out. I'm going to see you in another very good video.